Good afternoon. Welcome to part 2. In the first part, I showed 5 videos, short videos. What is physics, scientific method, models, controlled experiments, and dimensioning units. In this part, there will be 6 more, specifically accuracy and precision, measurement and parallax, rules for determining significant figures, rounding calculations, interpreting graphs, and evaluating physics equations. This is the first one, and it's about accuracy and precision. You need to understand the difference between accuracy and precision. Here we go.
Accuracy is the closeness of measurements to the correct or accepted value of the quantity measured. Precision is the closeness of a set of measurements of the same quantity made in the same way. Consider a game of darts. The target or accepted value is the bullseye in the center. The person who threw these darts is both precise and accurate. All the darts are grouped very close to the bullseye. This graph shows the results of an experiment that was repeated 4 times. Each time the mass and volume of the product were measured. We see that these results are both precise and accurate. They are clustered and very close to the expected value.
Okay, so the red dot is the expected value and the actual experimental values are really close by.
This set of throws shows that the dart thrower is precise but not accurate. The darts are grouped very close together, but they have missed the bullseye. Here are the results of another researcher's experiments. These results are precise. The data points are clustered close together, but not accurate.
So if you were to take an average of those measurements, the average would be pretty close, consistent. If you know about small standard deviation, but not close to the expected value. So this is precise but not accurate.
Each of these darts landed reasonably close to the bullseye, but the throws are not clustered together and are not precise. In this experiment, the results would average to a value close to the expected value, so they could be considered accurate. They are not, however, precise.
You could say that the error range is large when you're comparing it to the actual value.
Here we have a set of throws that are neither clustered together nor very close to the target. This set of throws is not precise and not accurate. These experimental results, likewise, are not precise and not accurate. When looking at experimental data, precision lets us know the experiment was done carefully in a controlled environment. Accuracy suggests that the experiment has accounted for all factors that might affect the system being studied.
Okay, so the next one is about measurement and parallax. You need to know what measurement, you know how to measure, but maybe not about parallax.
Some measuring devices, such as a meter stick, can appear to read different values when viewed from different positions. This phenomenon is known as parallax, and it can be a source of errors in measurement. If you measure the width of this window frame by keeping your line of sight directly over the measurement, you will find that it is 165.2 centimeters long. If you look from the right, you may report a measurement that is too long. If you look from the left, you may report a measurement that is too short.
Okay, so the next one is rules for defining significant figures. There's some significant zeros, excuse me.
Rules for finding significant zeros help you ensure that the numbers you report are accurate.
This is in your textbook as well, this table.
Zeros appearing between non-zero digits are significant.
Always. They're always significant if they're between digits.
We count these zeros when determining significant zeros.
So it is significant figures that we're trying to determine here as well.
Zeros appearing in front of non-zero digits, however, are not significant. We ignore these zeros when determining the number of significant figures.
One way to see it right away is the first one could be 3.52 times 10 to the negative 2. The next one would be 4.8 times 10 to the negative 3. And the last one could be 5 times 10 to the negative 4. So notice how I only said a certain number of significant figures when I read the numbers.
Zeros appearing to the end of the number and to the right of the decimal point are significant. These zeros are only written as part of the number when they are significant. Zeros to the left of the decimal place, however, have to be written whether or not they are significant in order to designate their place. If you measure exactly 200 milligrams of a substance, then the zeros in this number are significant. If, however, the zeros are just placeholders to indicate 200 milligrams, as opposed to 100 or 300 milligrams, then the zeros are not significant.
Okay, so the next one is about rounding. Rounding, to make sure you round correctly. Rules for rounding.
Rounding rules help you ensure that the significant figures you report in a measurement or calculation are accurate. Once we find the digit following the last digit to be kept based on the rules for significant figures, we ask the following questions. Is this number greater than 5? If so, we round up. Is this number less than 5? If so, we round down. Is this number equal to 5? If so, we have more questions to ask. Is the next digit after the 5 greater than 0? If so, round up. If the next digit after the 5 is 0, then look at the digit before the 5 and determine if it is even or odd. If it is odd, round up. If it is even, round down.
All right, and the next one is interpreting graphs. Be really good at interpreting graphs. So here we see 3 graphs. You're going to be learning in math, you'll be learning about the logarithmic graphs, and then you know probably already about linear relationships or parabolic relationships or exponential relationships.
The shape of a graph can tell you about the relationship between sets of data. This graph shows a linear relationship. As the mass increases, the volume increases.
Hopefully you remember the equation of a straight line, y equals mx plus b, where the m is the slope of the graph when you have a straight line. So this would be a linear relationship. And so there's an actual formula for the data here. The y-intercept here is 0, so that's why just mass is equal to volume times a constant, some number.
This graph is similar to the linear graph, except that it is not a straight line. It curves, becoming increasingly steep. This curve is characteristic of an equation in which one of the values is squared or raised to some power.
Maybe you remember in math equation what it looks like when you graph y is equal to x squared. Well, here we have no negative numbers, but if we did have negative numbers, this would be a parabola. So here you just have the right side of the parabola. So that's why it should make sense to you that you have a squared, one of the parameters is squared.
This graph has a steep curve that approaches but does not touch the axis. This curve is characteristic of an inverse square. As one value increases, the other becomes smaller.
And that's an example of inverse proportional. As one goes up, the other one goes down. So they're inversely proportional, if that always happens. Okay, and the last one is evaluating physics equations. And I'm going to do a separate video, hopefully, on dimensional analysis. So this is more like an introduction to that. Here we go.
Dimensional analysis and estimation help you to check the accuracy of your calculations. Suppose we are about to take a trip to a city 725 kilometers away. We expect our average speed to be 88 kilometers per hour. How long will the trip take? We first verify that we have set up the equation correctly by making sure the dimensions of the answer are what we expect. Only one combination of speed and distance will have the proper dimensions to give us the time. Does time equal speed times distance? No. Does time equal speed divided by distance? No, but since the dimensions of speed divided by distance worked out to 1 divided by time, we next tried the inverse equation. Does time equal distance divided by speed? Yes, this equation gives the correct dimensions.
So let's look at this one here. We've got time is equal to distance. Distance is length. So the first word on your left is length, divided by length times time. Remember that when you divide fractions, it's the same thing as multiplying it by its inverse. So you flip it over. So you've got length divided by time. Well, that's the same thing as length times, now flip it over, time divided by length. Okay, well, therefore, the lengths cancel out, and you end up with time.
To estimate the answer, we make an order of magnitude approximation by rounding each quantity to the nearest power of 10.
They just took 88 and say, okay, for one significant figure, that's about 100. 725, oh, that's about 1,000, because they decided there's only one significant figure.
We find that the trip should take about 10 hours.
Okay, notice how the kilometers canceled out. And if you have a parameter in the bottom in the denominator, you flip it over, that's why you get hours. Hopefully I'll be able to show that to you guys in class.
An exact calculation shows that the trip would actually take 8.2 hours, a number in keeping with our estimate and having the proper dimensions and units.
So that's all I have for now. Hopefully you guys can go through this, and this would be a review for chapter 1. See you next time.